All right. Hello, everyone. We are Group 30, and this is our project Chess Oracle, forecasting chess game outcomes from chess board states. I'm Samir Alizadeh, and with me I have Srinivas and Aditya. So, chess is a strategic game of foresight and positioning, predicting a game's outcome from a mid-game state challenges to distill key spatial patterns that determine success. So, the question we had was given as board state before the endgame, can we predict whether the game outcome ends in a win for black, white, or a draw without any move history or turn order to go off of? And so we used the Chezorite dataset from Newcastle University. It's a 3D tensor representations of board states from public games of 8 different grandmasters. It uses XY to represent the 8 by 8 quarter grid of the chessboard. Z has 12 channels, each representing a different piece type and color combination. And we use the labels 0, 1, and 2 for a draw, white wins, and black wins. So our input is the model only sees static board layouts at any given moment. The output is a multi-class labels of white wins, black wins, and draws. And it looks for it looks for patterns in material imbalance, positional control, and tactical threats that can indicate likely outcomes. So the model only sees a static board snapshot with no history or turn info, and it predicts outcomes based on positional patterns and not move sequences. It learns cues like material balance, center control, and king safety that we talked about above, and it struggles a lot with draws since they depend on repetition and stalemate, which is not visible in a single frame. And so we used the CNN to solve this problem statement, and did this because we can't use RNNs and LSTMs because there's no temporal interferences that are allowed. And the actual architecture is shown after the training analysis, and it is a little intuitive, so don't get too scared by how it looks. And so as you can see here, we're comparing our random forest confusion matrix and our CNN confusion matrix, and we see that CNN clearly outperforms random forest across all classes. CNN reduces confusion between draw and white wins, and the random forest shows moderate confusion between all classes, specifically draws versus white wins.
And here's the model that we've used for our final presentation. We see that even though it's like pretty deep in architecture, it's also very intuitive. We are just using 2 residual blocks. And one important call out probably would be that we're inducing a bit of the early information into deeper stages of the CNN, where we take meta information like piece counts, piece differences, and then induce it later on to improve the inferences that we generate. One other call out would probably be that to increase the amount of data that we had to augment by flipping the both states and then also mirroring the both states. Some of the optimizations that we did was we changed the number of CNN layers, tinkered with the drop rates and then the batch sizes. This helped combat the overfitting problem that we had. We also experimented with a lot of deeper networks. Here are some of the results that we had. You can see that it was performing a bit better than the random forest baseline that we had. But in order to experiment a bit on whether draw indeed was the problem for getting the inferences, we did a bit of masking. Here is us masking the draws. You can see that it's getting better results. And then if we mask the other states, you can also see that it drops a bit in performance. Here's the training curves and confusion matrix. Um, you can see that it's pretty similar across the board, but if we mask the draws, it's clearly better. We did a demo during our live presentation. You can check that out. It shows that we had a complete product, but in comparison to the baseline, we can clearly see that there's a 15% improvement comparing to the random forest. Some of the key takeaways would probably be that it's struggling with draws because we can't get temporal information. We can just use spatial information. But in order to improve our model, we can probably induce meta information like time on clock and stuff like that. None of the team members that we had worked on this data set before doing this challenge, but we got pretty good results with the CNN that we experimented on. And then we got a pretty good score that is better than the challenge baseline. And here's the reference. Thank you for listening to our presentation.
Thank you.
That we were referring to. Um, this is a game that's taken from a Title Tuesday match that took place recently. It was a match between Magnus and Alexei. You can see that Magnus won at the end. And we just used our application to annotate the both state. So it's just a one-to-one of the board state, and then when we click on the get board array, you can see that it spits out the board representation at the same time, predicts who's going to win. It works perfectly fine. So yeah, that's the demo that we were referring to. One more thing would probably be that a lot of people asked about how this 12 captures all the piece information and the colors. The first 6 represents the uh, white pieces, and the last 6 represents the black pieces, and each of the um, dimensions in it represents a piece. So that's how you get both the color and the piece combination. Thank you.